In this module we will discuss more on concepts and calculations on thermal properties of matter. The conditions in which a particular material exists are described by physical quantities such as pressure, volume, temperature, and amount of substance. As an example, we have the ideal gas equation, where P is the pressure, V for volume, N is for the number of moles, R for the gas constant 8.3145 J/mol.K, and T for temperature. Ideal gas is different from a real gas since it is purely theoretical, but it is necessary to get an understanding on the nature of the states of matter at a condition where temperature is involved. Here we have two conditions where a gas of N molecules is contained in small volume V1 and the same number of molecules put at a larger volume V2. By taking the ratio of pressure times volume over temperature, the number of moles times the gas constant remains the same for both conditions as shown in equation 2. We can then equate the two systems and get equation 3, which is useful in solving problems where the same amount of gas is subjected to a different size of container, pressure, and temperature. As mentioned earlier, ideal gas is theoretical that we need in order to have a basic understanding on the nature of gas. Here we compare an ideal gas and real gas properties. Here we list the properties of an ideal gas. First, its particles do not interact with each other or have no intermolecular forces. Its gas particles have negligible volume. Its gas particles are equally sized despite being different from one another. Its gas particles move randomly in agreement with Newton's laws of motion. The collisions of gas particles are perfectly elastic with conservation of energy and conservation of momentum. Here we have the properties of real gas. The particles interact with each other with intermolecular forces. Repulsion when the particles are too close. And attraction when they are far apart. The gas particles have definite volume and the particles have different sizes for different types of molecules. The gas particles move randomly in agreement with Newton's laws of motion just like in ideal gas, but the collisions are not perfectly elastic. Real gas can be described mathematically by using van der Waals equation as shown here. Real gas describes a state of material that includes the interaction of molecules between themselves. In the equation, A and B are empirical constants that are determined experimentally and are different for different gases that define these interactions. Although ideal gases are purely theoretical, real gas can behave like it at certain conditions. To have less intermolecular interaction we have low pressure A and high temperature. Both conditions promote less intermolecular interaction by increased separation of particles. Here we have an example. A cylinder 1 meter tall with inside diameter 0.12 meters is used to hold acetylene gas, molecular mass 26.04 gram per mole, for welding. It is initially filled with gas until the gauge pressure is 1.3 times 10 to the power of 6 pascals and the temperature is 22 degrees Celsius. The temperature of the gas remains constant as it is partially emptied out of the tank, until the gauge pressure is 2 times 10 to the power of 5 pascals. Calculate the mass of acetylene that has been used. First we calculate the volume of the container, which is a cylinder. We divide the diameter from the given by 2 to obtain the radius. The cylinder remains constant after the acetylene gas has been used. Note that the volume of the cylinder is given as pi times square of the radius times height. Substituting the values from the given and calculated, we have the volume of the cylinder around 3.6 times pi times 10 to the power of -3 meter cube. It is shown in equation A. Note that the gas has been released at constant temperature and constant volume. The processes involved here are isothermal or at constant temperature and isochoric at constant volume as the gas is used. Since the temperature is constant then, the temperature before the gas is released, or T1, is equal to the temperature after the gas has been released, T2. This is equal to 22 degrees Celsius. We convert this to Kelvin scale by adding 273 Kelvin and we have 295 Kelvin. Similarly, the volume before and after the gas is released, the volume V1 and V2 are equal. The mass used, noted as mu after it has been partially emptied, is equal to the initial mass m1 minus the mass remaining, or m2. We write this as equation B. We rewrite the ideal gas equation to solve for mass m and take into consideration the relation of molar mass, and we have equation C. We consider the condition for mass m1 and mass m2 and substitute this equation B, which we then substitute the values obtained earlier, and we have the value of mu. Here we see that the mass used or released into the atmosphere is about 132 grams. Let us look at the pressure volume of ideal gas and real gas. For the ideal gas, we plot the equation 1 at different temperatures with increasing value. The curves are called isotherms. At various constant temperatures it is expected to obey the ideal gas equation, where the pressure is inversely proportional to the volume. When pressure decreases, the volume increases, and vice versa. Here we have the pressure volume graph for a real gas. The red-colored isotherm curve defines the critical temperature Tc. Below critical temperature, say T2, the isotherm develops a flat region. In this region, we can change the volume without changing pressure. Under the shaded curve, the state of the matter is in liquid-vapor equilibrium. This means that at this region liquid and gas coexist, and it is also known as the biphasic state. Kinetic molecular gas model of an ideal gas that describes gas under closed space. Number 1, the container of volume Va will contain a very large number N of identical molecules, each with the same mass m. We see here represented by the dark blue circles. The size of these particles are exaggerated for visual purposes. Number 2, the size of these molecules are very small in comparison to the average distance between particles and to the dimensions of the container. We write it as the radius of the particle is very less than the distance between particles and very less than the radius of the container. Number 3, the molecules are in constant motion that are governed by Newton's law, and they collide elastically with the walls of the container, and number 4, the container walls are perfectly rigid, infinitely massive with no tendency to move, and the particle simply bounces off with an equal magnitude of speed but opposite in direction. Let us look at the behavior of the particle AST. It collides with a rigid wall. Here we have a particle that collides with the wall at an angle and bounces later after collision with the same angle. Examining the component of the vectors before and after collision, we see that before collision its velocity along the x-axis is a negative vx and along the y-axis it is a positive vy. After it bounces from the surface of the wall, the magnitude of its components are the same. The direction along the y-axis after collision is still positive since the particle is moving upwards. However, the velocity along the x-axis is positive, which is opposite compared to its before collision. Recall the conservation of momentum equation. We see that along the y-axis the change in momentum is 0, but for the x-axis it is equal to 2 times its mass times its velocity along the x-axis. Therefore the total of its momentum delta p is equal to the sum of its components, which is equal to 2 times its mass times its velocity along the x-axis. Let area A on the wall collision occurs. The type of collision is perfectly elastic. N is the number of particles on the cylinder over a small period of time dt. The length of the wall is given by d equals vx times dt with the volume shown in equation 6. We assume that half of these particles are in collision with the wall. The total number n of particles in collisions and bouncing off the wall given as equation 7. Then half of that must be the number of particles in collisions, so we divide it by 2 and get equation 8. For a single particle bouncing off a rigid, the momentum equal to 2 times mass times velocity as shown in equation 5. So for the total change in momentum for n particles over a short period, dt is equal to n over 2 times the momentum of a single particle. We then substitute the n/2 equation, we get an expression of dp over dt, or the change in momentum over time, shown in equation 9. Recall from Newton's first law in terms of momentum, which is force is equal to dp over dt, and the relation of force and pressure given as force is equal to pressure over area. Substituting the previous expression for total change in momentum, we get equation 9. We then rearrange this to obtain an expression of pressure shown in equation 10. This pressure is the one exerted by the particles hitting the surface of the wall, where each particle exerts a certain amount of force. The velocity of the individual molecules inside the cylinder is not constant or the same. Therefore, we replace velocity squared by its average value, which is related to the average speeds of the molecules. Substituting this average velocity, we get that the pressure times volume is equal to 2/3 times the kinetic energy function of the individual particle with mass m, as shown in equation 11. This kinetic energy term in equation 11 is called the translational kinetic energy. We rewrite this expression shown in equation 12 and equating this to the ideal gas equation and obtain equation 13. Rewriting equation 13, we get equation 14, and the equation shows that the kinetic energy increases when temperature increases. Boiling water is a good example for this. When you heat the water molecules, the motion of the particles increases as indicated by the rapid boiling motion of water. This eventually escapes the water surface when it is hot enough and goes into a gas state. Here we will do some rewriting of the ideal gas function. Boltzmann constant, denoted by K, is the factor that relates the kinetic energy average of particles in gas with temperature. Here we rewrite the ideal gas equation to incorporate this parameter. K constant is given as the ratio of the gas constant R over Avogadro's number, as shown in equation 15. Substituting this to the kinetic expression equation 14, we get that it is expressed as 3/2 times n times the Boltzmann constant times the temperature. We note that the expression pressure times volume is equal to 2/3 times kinetic energy, shown in equation 12. We incorporate this, and in terms of the Boltzmann constant, we have the re-expression of the ideal gas equation shown in equation 15. Here we write an expression for the root mean square speed. We start with the energy equation 14. From there we consider the velocity in kinetic energy as the average speed, since particles inside the volume have different magnitudes. Rewriting this equation and setting the 1 over m to n over mass m, we get an expression of the average squared. The root mean square speed is the square root of the square of the v average. This is shown in equation 16. In terms of the Boltzmann constant, we have equation 17. As particles move in space, we take into consideration the mean free time and the distance, or the mean free path of the particle. The mean free time, shown in equation 18, is the average time for molecules to collide elastically with the wall. The average distance, which is the product of the speed of the molecule times the mean time, as shown in equation 19. Here we have an example. We are asked to determine the RMS speed of the molecules of hydrogen gas at room temperature, or 300 Kelvin. The solution is done by using the equation for the root mean square speed of the gas using equation 16. And the speed of the hydrogen gas at room temperature is about 2000 meters per second. Here we tackle the molar heat capacity CV relation to ideal gas equation. Recall the relationship between temperature and kinetic energy shown in equation 14 and the equation for the heat energy, where the constant is shifted to molar heat capacity with units in joules per mole Kelvin. This is at a condition that is constant volume or isochoric process. Taking these into consideration and assuming no other quantities interfere with the heat and kinetic energy, the change of heat and change of kinetic energy are expressed in equation 20. This formulation defines the relationship between the molar heat capacity at constant volume and the fractional ratio of the gas constant R for an ideal gas. Calculating the value of the molar heat capacity, it is shown to have a value of about 12 joule per mole Kelvin. Shown here are the molar heat capacities for the three types of gases, the monoatomic type, diatomic type, and polyatomic type. Comparing the value of the molar heat capacity calculated from equation 20, it appears that only the monoatomic type of gas fits this value. Equation 20 is related to its degree of freedom of the molecule, which we will show later. For diatomic or linear molecules, we use the equation here and its molar heat capacity is about 21 joule per mole Kelvin. This is comparable to the diatomic type of gases. However, the polyatomic or non-molecule does not appear to fit well. The value obtained is for the ideal gas type of polyatomic molecule. Polyatomic molecules have higher than the predicted value of molar heat capacity due to its complexity of degrees of freedom that increases its value. Translational degree of freedom is the ability of a molecule to move freely in space. Shown in the figure is a monatomic molecule moving in three-dimensional space. For this case it is in a Cartesian coordinate system. The motion is with respect to its center of mass and for this case is in the middle of the mass due to symmetry. The particle is able to move along the x, y, and z axis, which is the 3 degrees of translational freedom. This translational motion is present for all gas molecules. It applies to monoatomic, diatomic, or polyatomic types of molecules, so that means they all have 3 degrees of translation freedom. Rotational degrees of freedom is the ability of the molecule to rotate in unique ways with a change in its orientation. Monatomic gases do not have rotational degrees of freedom since it does not have a change in its orientation. Basically, it would appear the same even if it is rotated, and this is because its center of mass is in the middle position. Diatomic or linear molecules have 2 rotational degrees of freedom, which are the ones not intersecting the 2 atoms and its center of mass. Polyatomic or nonlinear molecules have 3 rotational degrees of freedom. Vibrational degree of freedom is the ability of a molecule to vibrate by stretching, compression, and bending of its bonds. Monoatomic molecules have no vibrational degree of freedom since they have no bonds to stretch, compress or bend. Diatomic molecules have 1 vibrational degree of freedom, which behaves like a spring and oscillates in simple harmonic motion. This vibrational motion of the diatomic is dependent on the temperature. When the temperature is low enough, then the contribution of this motion is negligible. Polyatomic molecules can have many atoms and the number of vibrational motion is given as a function of 3n minus the translational and rotational degrees of freedom. Vibrational degree of freedom. Degree of freedom of gas molecules is the total number of independent modes in which it can possess energy through motion. For monoatomic it has a total of 3 degrees of freedom and is transnational in nature. Monoatomic molecules have a total of 3 degrees of motion. Diatomic or linear molecules have a total of 6 degrees of freedom, but at low temperature its vibrational contribution is negligible, so it is reduced to 5 degrees of motion. Polyatomic or nonlinear molecules have a total of 3n degrees of freedom. Energy associated with degrees of freedom. Note that the average energy for a monatomic is given as the equation shown. This value of average energy is related to its degrees of freedom. Each degree of freedom has an average energy associated with it, and it is 1/2 kT or 1/2 RT. This energy is in the form of kinetic energy and potential energy. For one translational degree of freedom, its energy is 1/2 kT or 1/2 RT. For one rotational degree of freedom is 1/2 kT or 1/2 RT. For one vibrational degree of freedom is kT or RT. Considering the vibrational motion between bonds, it has two atoms that oscillate against each other, so its energy and both potential and kinetic energy, the energy of vibration, involve 2 degrees of freedom, so that vibrational motion in a molecule is associated with energy is equal to 2 times 1/2 kT equal to a kT. Note that at room temperature the contribution of vibrational energy is ignored. The total energy for a molecule is the sum of the energy contribution from translational, rotational, vibrational, and electrical. Here we summarize the energy contribution of the linear molecules and nonlinear molecules. We see that the energy contribution has 2 conditions. The first one is at room temperature, where the vibrational degree of freedom is inactive or negligible. The total energy at room temperature, where we neglect the contribution of the vibrational and electrical, is equal to 5/2 kT for linear molecules. For the nonlinear it is 3 kT, and for n number of molecules we have energy total as n times 3 kT. Limitations of Dulong-Petit law. The Dulong-Petit law is only relevant to the heavier elements. It is only applicable to elements that are in solid form. It cannot be applied to lighter elements having high melting points. It only gives a rough atomic mass. Previously we already derived the root mean square speed. So, here we tackle molecular speeds such as most probable speed and average speed. Generally, molecules move with various speeds, thus we need to modify our results in the kinetic molecular model on the ideal gas. The model we use to do this is the Maxwell-Boltzmann distribution. It is a distribution of speeds among the gas particles at a given temperature. At different speeds we see the behavior of the probability distribution. As the temperature increases, the curve flattens and shifts towards higher speeds as shown by the red graph. The figure shows the Maxwell-Boltzmann distribution of the magnitude of velocity of gas molecules. We see the relationship among the different speeds. The most probable speed is greater than the average and root mean square speed. Equation 23 shows the expression for the Maxwell-Boltzmann distribution. Differentiate the MB distribution function with respect to the magnitude of velocity v. To solve for the solution we consider the obtained derivative equal to 0. For this equation to be 0, we examine 3 terms where we can replace values of speed v. The first term, which is an exponential, cannot be 0 for any value. So we consider the second and third terms as shown here. Thus, we have 2 possible solutions. For speed equal to 0 would be the minimum value from the Maxwell-Boltzmann distribution. So we consider the second option and we get equation 25, the formulation for the most probable speed. We can rewrite this also back to in terms of the gas constant shown in equation 26. At high temperatures where the graph flattens, the value of most probable speed is roughly around the middle of the graph. Here we derive the average speed of the particles. We calculate this by taking the integral of the Maxwell-Boltzmann distribution shown in equation 23. We simplify first the equation by setting the parameters a and b, which are constants, and get a simpler version shown in equation 24. To integrate this, we again set the L and dl function and use partial integration shown in equation 25. By setting the parameters, we have equation 26, which is the partial form for the equation. We now operate the integral for the different terms in the range from 0 to infinity. We get that the average speed is shown in equation 27. We then substitute back the values of a and b constants. Further simplifying the equation by substitution, we continue until it is reduced further. Finally, we arrive at an equation of the average speed of gas shown in equation 28. We can also express it in terms of the gas constant R shown in equation 29. That is it for now, and I hope you learned something new today. For questions and comments, you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and a class section. Thank you for listening, and see you next module.